In this topic, we will learn how to apply first-order differential equations to solve some applied problems. From my experience in mathematics courses, students are usually interested in applications of the concept that they are working with. However, usually applications are more difficult. The thing is that for applications, you need to come up with the correct differential equations, and then you need to solve it. In the previous topics, you are given a certain equation, then you choose the appropriate method to solve. Here, you need to come up with the correct equation as well. There's a variety of problems that can be solved using differential equations. However, we will be working with only a few of them. So the first one, which you may have seen already in one of the previous topics, you may pause the video and read the problem. But essentially what it says here is we have an object that's falling from atop the building. And we want to write out the formula for the velocity of the object. And velocity is denoted by Vt. T is time. Now, all right. So how do we do this? Let me just write down. Yeah. Say at time t equals 0, the object is at the top of the building, and it stayed like that. But when t positive, the object is falling at certain and it's at a certain position like that. So to write out the equation for the velocity, we need to use Newton's second law, which we saw earlier. The forces that are acting on the object are gravity, denoted by Fg, and it's just mg. And by the way, as before, we're going to choose the positive direction to be here. So positive direction. Everything going down is positive, and quantity that going upward would be negative. And then we have another force, that the air resistance, denoted by Fd, D for drag. And the assumption over here, the air resistance is proportional to the velocity with resistance constant k. So proportional means that it's k times v, but because resistance is upward, we have the minus in front here. All right, so these are the two forces that we use. And then we have Newton second law, which says that m times acceleration is the total force acting on the object. Total force. So we may rewrite that m times a equal to, we have two forces here, mg and then minus kv. We are given the values of m and k and g, but we will use those later. Now, a acceleration is derivative of velocities, dv dt. We have mg minus kv. And now we have a differential equation, the ODE. what unknown v, which is a function of time. Um, so to solve this, let's put the values in m given above as 2 kilograms, k is 4, and then g is 9.8. So we don't need to care very much about the units here. All the units are matched up. Uh, so it's going to be 2 dv dt equal to m, again 2 times 9.8 minus k is 4. Now, as usual, we should solve for the derivative, and then we will determine what type of equation we have. Dividing everything by 2, we have 9.8 minus 2v on this side. What kind of equation is this? It is a linear equation because we can rewrite the equation in the form dv dt plus 2v equal to 9.8. Now, before solving, let's look at initial condition. What initial condition do we have here? Initial condition comes from the fact that when t equals 0, the object is at the top of the building, so it's not moving yet. And because of that, we have v at 0 equal to 0. When t equals to 0, v equals 0 as well. Now, let's solve the ODE above. You see linear equation with plus 2 here is our p. This time t is the unknown, is the independent variable, so I'm gonna write p t, and q t is the right hand side. You may pause the video and try to solve this equation. And we have integrating factor mu of t is e to the integral of p dt. Now I want you to write out carefully. Whenever you have integral, you should have dt or dx. I noticed that some of you didn't do that, but you should. Then we have e to the 2t. And then we multiply standard form by e to the 2t. Remember that this equation is standard form because we have just 1 times dv dt. So we will have e to the 2t dv dt plus e to the 2t and tv equal to 9.8 e to the 2t. And as usual, this side is the dt of product v times the integrating factor, which is e to the 2t. And then we integrate. We have v e to 2t equal to 9.8 e to the 2t dt. And so we get 4.9 e to the 2t plus c. On the left side, we have v e to the 2t. Now using initial condition, t equals 0, v equals 0, plug in, we have 0 equal to 4.9 e to the 0 plus c. E to the 0 is 1. So from here, we see that C is minus 4.9. And then we plug C equal to minus 4.9 back in. And we have V times e to the 2t equal to 4.9 e to the 2t minus 4.9. And now to solve for V, we can multiply both sides by e to the negative 2t, or which is the same as dividing both sides by e to the 2t, either way. And the answer you get is this. This is the formula for the velocity of the ball of the object at time t. So as you have seen above, one of the main steps is to come up with the correct differential equation using certain laws from physics. And for a falling object, in this example, we use Newton's second law. We're now looking at another example. You may pause the video and read the problem. But essentially, what it says is that we have a cup of coffee with a certain initial temperature, in this case 200 degrees, and the coffee is cooling down in a room with temperature 80 degrees. And we are given a constant K, which I will explain later. We need to write down the differential equation and then determine the formula for the temperature of the coffee. To solve such a problem, we're going to use something from physics called Newton's law of cooling. And what it says is the following. The rate of change of the object's temperature is proportional to the difference between the ambient temperature and the object's temperature. Now, that's what the law says. But in order to solve the equation, we need to write out the formula for the law here. Now from above, we use U to denote the temperature of the object. So this is the rate of change of the object temperature from calculus 1. The rate of change means derivative. So we have du dt equal to proportional. Proportional means we have a constant times proportional to what? Proportional to the difference between the ambient temperature. Ambient temperature means temperature of the room or temperature of the surroundings. I will denote this by a difference, a minus the object temperature, which is U. So this is the formula where here A is ambient temperature So knowing this formula, Newton's law of cooling, we can write out the differential equation. So for our problem, I should change back to black here. K is 0.01, and then the ambient temperature is what, 80 degrees right there. Room, the temperature of the room, that 80 degree. So our equation is du dt equal to 0.01 times 80 minus u, which we can distribute in, and we get what, 0.8 minus 0.01 u. There is initial condition as well. Initial conditions is given that initial temperature of the coffee is 200 degrees, meaning that when T equals 0, U equals to 200. We have our ODE right here and the initial condition. How do we solve this equation? What type of equation is this? This is a linear equation, because we can rewrite du dt plus 0.01 u equal to 0.8. Now, in fact, this equation is also a separable equation. You can try to think about that. I prefer using the method of linear equations to solve this. P of t here is 0.01 and Q of t is 0.8. So integrating factor, mu of t is E integral of 0.01 dt. Don't forget the integral. And so we have E to the 0.01 t. The equation above is in standard form. So we multiply through by the integrating factor. In this case, the integrating factor is e to the 0.01 t, and so we have e to the 0.01 t du dt plus e to the 0.01 t 0.01 u equals to 0.8 e to the 0.01 t. As before, the left-hand side is derivative of product, which is u times e to the 0.01 t, and the right-hand side we have 0.8 e to the 0.01 t. Now we integrate. We have u e to the 0.01 t is the integral of 0.8 e to the 0.01 t dt. Right, so how do we get the integral? 0.8 is a constant. The integral of e to the 0.01 t will be e to the 0.01 t divided by 0.01 plus c. So we simplify as u times e to the 0.01 t equal to 0.8 divided by 0.01 will be 80, and e to the 0.01 t c. At this time, we use initial condition t equals 0, u equal to 200, and we solve for c. And I need to add another slide in. So we have 200 e to the 0 equals to 80 e to the 0 plus c. E to the 0 is 1. Solving this, we have c is 120. And as usual, we plug c equal to 120 back in, and have u e to the 0.01 t equals to 80 e to the 0.01 t plus 120. Now solve for u by multiplying both sides by e to the negative 0.01 t. Then we will get 80 plus 120 e to the negative 0.01 t. And this is the formula for the temperature of the coffee at time t. Now look at another example. We have an ice cube with initial volume of 8,000 cubic inches, and the ice cube is melting. And we are given that the ice cube is melting at a rate equal 2 times the surface area. And we want to find the formula for the volume. So let's see how we do this. Now we let Vt to be the volume of the cube as time t. So first, what does it mean? 8,000 cubic inches here. V will be, the unit for V will be in cubic inches, but we can ignore the unit now. Let's say that t equals 0. At time 0, V equals to 8,000. But let's write out the differential equation. The differential equation comes from the following sentence. The ice cube is melting at a rate which equals 2 times of the surface area. Rate means derivative. We have dv dt equal to 2 times the surface area. But be careful, even though the problem doesn't say, it says surface area at time t here. Because it will not make sense to say that the rate of melting is always 2 times the surface area at the initial time, right? When the cube gets smaller, it's melting slower. When the cube bigger, it's the rate of melting is faster. Like what it means. Another thing, the cube is melting, so the volume is decreasing. Decreasing means that the derivative is negative. So even though the problem doesn't specify clearly, we need to know that there's a minus sign in front. All right, so let's see how to write out the differential equation. Let's draw a cube here. Now what I'm drawing here is not the cube at initial time 0, but a cube at a time t, a certain time t positive. Uh, when t equals 0, we have a bigger cube with 8,000 inches, but here is time t positive. Uh, so the volume will be V, and let's say we have the size x, and x here. Again, at time t, x is not the initial one. So we have the formula. Surface area is what? How many sides do we have? We have 6 sides for the cube, and each side is a square, x by x. So we have 6x. Okay. But also the volume is given by x cubed. Now let's look back at the differential equation. What it says that dv dt equal to minus 2 times the surface area, which is 6 square. But well, we cannot solve this because it involves two unknown v and x, right? So to solve the differential equation, we're looking for v, so we should convert everything to v. How to do that? From here, we take cube root. We have x is cube root of v, or v to the 1/3. Now put it here, we will have minus 12x squared, and so x is v to the 1/3. So x squared is v to the 2/3. And this is a ODE that we're looking for. The differential equation for the unknown v. What type of differential equation is this? It is a separable equation because we can separate two sides by dividing both sides by v to the 2/3 and then multiply both sides by dt. We have minus 12 dt here. And now integrate. How do we integrate? The right side is easy, minus 12t. Don't forget to add c. And on this side, we need to use the power rules by writing v to the negative 2/3 dv. So the integral will be v to the negative 2/3 plus 1 divided by the new exponent, so negative 2/3 plus 1. But the rule integral of v to the n is v to the n plus 1 divided by n plus 1. Simplify this, we will have v to the 1/3 and then divide by 1/3, which is the same as multiplying by 3. So we have this. Use initial condition, which says that when t equals 0, v is 8,000. Plug in, we have 3 8,000 to the 1/3 is minus 12 times 0. Let's see, this is gone. And here the cube root of 8,000 is the 20. So C is 60. Now we put C back in. And then we try to solve for V. We get 3 V to the 1/3 is minus 12t plus 60. Now to solve for V, and we add another slide. Divide both sides by 3. We have V to the 1/3 is minus 40 plus 20. And raised to the power 3, we have the formula for E. And this is the formula for the velocity of the cube as time t. So we see that when is v equals 0, the problem doesn't ask, but we can see v equals 0 when we solve this equals 0. So t equal to 20 over 4, which is 5 units of time. The problem doesn't specify what it is. But if the unit for time is minute, then it's 5 minutes here.